In this module, we are going to see how we are going to use the basic three equations that we have related to velocity, time, acceleration, displacement, and so on and so forth. The more popularly written equations are V is equal to U plus AT. V is called the final velocity. This is called the initial velocity, and this is called the acceleration, and this is the time. Remember that this acceleration A is a constant in this equation. Now when we want to give the vector form of this, then we understand that each one of them have arrows on the top of it to tell that they are vectors. Time doesn't have an arrow, so it's a scalar. LHS is a vector, so entire RHS is a vector, and we understand here we are multiplying a number with a vector. It is a vector. This vector is added to another vector, so you get another vector. That vector is this. So when I want to take this part here, then we say A bar into T is V bar minus U bar, which we previously called it as delta V. That's called change in velocity. Friends, let us try to understand that previously I have written it as Vf minus Vi. This Vf is called the final velocity, and this is what is called the initial velocity. Here we are just multiplying the time with a number. So what it will do, it will increase the length of that vector, that's all. If this number is less than 1, then it is going to shrink the line. If it is more than 1, it will increase the line of that vector, but has no role to play to change the direction of that vector. So let us try to go back here by writing that A is equal to dV upon dt, and so I can always write it this way. So dV is A dt, so we can integrate both the sides. You are able to see that this A has been pushed outside the integral, which means that this A is not a function of time. When it's not a function of time, we can treat this as a constant. The variable here is the velocity, that when the time was 0, let the velocity be U. When the time is t, let the velocity be v. So this part of it becomes v minus u, and this will become, so we have this beautiful relation. So once you go with this, you will realize that this A is a constant. Constant, when I say, independent of time. That's a very important part of it here. So we have this equation. We can also write this acceleration, which was dv by dt, as a dv by dr into dr upon dt, and still it is dv by dt. So now I can say that this is dv upon dr into v. Friends, remember that we had velocity as the rate at which the position vector changes with time. So we can write this v dv is a into dr. Remember, this a is still a constant here. And when I want to integrate, I push it outside the integral, and this is what is u when the position vector was at ri. When the position vector is at rf, then the value is called v. So this value turns to be v square by 2 u square by 2 a into rf minus ri. We already told that change in position is displacement. So from this relation we get that v square minus u square is 2as. Remember, a is a constant, and this S is what is called the displacement, which we can write it as Rf minus Ri. So that's where it is.